It's our pleasure to start off this Meow Spring 2026 seminar series with a talk on certified combinatorial optimization by Andy Oertel, and this will also double as the half-year pre-defense seminar with Andy. So the first half will be more like the pre-defense seminar, and then, as we usually do after the break, we'll have a more technical second half. So Andy, please take it away.
Yes, precisely. So thank you. So let me start off by introducing to you what combinatorial optimization is. So in combinatorial optimization, we have an input problem which is defined through an objective function that we want to minimize, and for simplicity, let's just consider a linear function. And second, we have constraints, or we have only a set of feasible solutions. And for simplicity, let us just consider the integer points inside the convex polytope. So everything is nicely linear. And then for this object, for this objective function and this set of solutions, we might ask, well, we maybe don't have this set of solutions explicitly, so we might want to know if there are even solutions, if the set is empty or not. Additionally, what we might be interested in is to find the optimal value, the optimal solution, an optimal solution. Or we want to enumerate all optimal solutions, or just have a count of how many there are. And this idea of having this very general formulation has really been a success over the last couple of decades. So just to name a few, there's like this satisfiability solving, Boolean satisfiability SAT. There's constraint programming, there's mixed integer linear programming, and all of them have improved a lot. And nowadays, this approach of having a modeling a problem inside with this very general language and solving a problem through very general solvers is used all over the place for scheduling, logistics, hardware verification, even proving mathematical theorems. So this idea is really big, and it's really nice to use, and we can solve very complex problems very easily. The only issue is, well, these solvers, they are sometimes wrong. It's also just software. So software has bugs, and even the most best commercial solvers, they are buggy, and it's well documented that there are issues in these solvers. So how can we make sure that the result returned by the solvers is correct, that we can trust this result? And the first idea you might think about is software testing. So we have known inputs and output pairs, so what we expect as a result. And then we check if the returned result by the solver matches the expected output. However, the issue here is that, well, we only can show the presence of bugs, but not the absence. We have no guarantees except for the test cases that we tested. The other extreme would be formal verification. And here we have a formal specification on what the solver should do, what the software should do. And then we get proven guarantees that the solver adheres to the specification. However, this approach is very complex and complicated, and it's completely out of reach for efficient model solvers. And so what we propose is a middle ground, which is called certifying algorithms, which gives you guarantees, formal guarantees on the correctness of the result. We know nothing about the solver, but the result we have guarantees on. And additionally, it's not too difficult to do, and it's actually possible to do for the more efficient modern solvers that we have nowadays. So what is the idea of certifying algorithms? The idea is that the solver not just gives us a result, but it also produces a certificate. And the certificate shows that the result is correct. And then we can give this certificate together with the result and the input problem to a checker. And this checker then verifies that the result is correct using the certificate as a hint, or as an aid to basically make it easier in checking than actually the solving process, so that we give all the hints to the checker so that this checking process is very easy. And then this checker can verify to us that either the result is correct or we checked. And well, we would like to do this now for these combinatorial optimization solvers. But as I told you they're like very different. There's like SATs, mixed integer programming, and so on. So maybe we first look at like one specific problem. And this one specific problem that we look at is pseudo-Boolean optimization. And this is like a special combinatorial optimization problem where we're given as input a linear function as objective function, and our constraints are also just linear, integer linear inequalities that restrict our space of or set of feasible solutions. And additionally, also the variables, they are just in the domain 0, 1, so everything is Boolean. And this is known as a pseudo-Boolean optimization problem, or sometimes also, or like in the operations research community, also known as the 0, 1 integer linear program. And then, for example, we can ask about this problem, what is like the optimal solution, like minimum, like the solution that satisfies these constraints, such that we minimize the objective function. And here, for example, the minimum, the optimal value would be 2. And this we can see by setting x1 and x4 both to true, as they don't appear in the objective. And then we still have to set x2 or x3 to true, but then it's cheaper to set x2 to true or to 1. So how does it help us now? So like the goal is we want to have certifying combinatorial optimization solvers for as many paradigms as possible. And the good thing is now that, well, or the issue is that we have like all these different problems and solvers and paradigms. And how can we unify them? And the idea is that, well, we can basically encode a lot of combinatorial optimization problems into each other. And maybe let's just use pseudo-Boolean optimization as like a nice middle ground to encode our problem into. And then we express the reasoning of the solver just as pseudo-Boolean reasoning. And so, but then the certificate, it argues about like reasoning with this pseudo-Boolean problem. However, the solver itself, it still remains the same. So we only add the certificate writing to the solver. We don't change anything about like the reasoning in the solver itself. Only the certificate writing knows about this like pseudo-Boolean problem. So anything else in the solver, it remains the same. So it's only just adding some print statements. And the nice thing is that because our certificate just talks about the pseudo-Boolean problem, is that we just need one checker for all of combinatorial optimization. And then this very PV system that I will present here today, it's basically this unified certification system using pseudo-Boolean optimization. So for the rest of the talk, I will first tell you a bit, or for the first part, I will tell you first a bit more about certifying algorithms, what they are, and what we know about them. Define them a bit more formally. Then we will talk about certification for combinatorial optimization, so this very PV system. In the third, then I will talk a bit about my contributions, my papers that will be included in my PhD thesis. And this will also lead us to applications where we use this certification system. And at the end of the first part, I will conclude with some future work. So let us start by defining certifying algorithms more formally. So again, we have this same diagram as before. It's just printed a bit slightly differently. But we have still the input to our algorithm here, and we have an output to the algorithm, and then we have this checker. An important thing as well, we want to compute a function, and then the algorithm, the certifying algorithm, and the checker have to be for the same function. Like I cannot like compute an algorithm for division, and then the checker is for multiplication. That doesn't work. Like it has to be the same things that are computed. And then to define what our certificate looks like, we first say that we have a precondition at our input. Our input has to satisfy a precondition. And then our output has to satisfy a postcondition, what we expect as output from this function. And then the certificate, what it does, it basically either shows that the precondition is not satisfied, so that this is not a valid input, basically, or it shows that the postcondition holds, saying that, well, we computed correct output if like this precondition holds. And an important thing is, or important note for the checker here is that, well, if the checker accepts, then we have a formal guarantee, or we have a guarantee that the output is correct. However, if the checker rejects, so does not accept this check, then either then the certificate or the output is wrong. Like, but we don't know which one. Like, it can still be that the output is correct, that the algorithm outputs the correct value, or like returns the correct output, but the certificate is just wrong. So to give you a better idea, or again, to give you a better feeling, let's us consider an example of what this means: precondition, postcondition, certificate. So let us consider the example of division. And so the problem is we want to divide a number n by d. And let us just say both numbers n and d are rational numbers. So then the precondition is, well, we cannot divide by 0, so the precondition is that d is not 0. And then the postcondition is that, well, we want to get a rational number n divided by d as like the output, or if this if d, the divider, is 0, then we get a special character bottom that just says like invalid input. And so we implement now a division algorithm, and it returns like in the output y for the input n and d. So how can we now check that we have that y is in fact n divided by d, or this bottom character if d is 0? Any ideas what we could do?
Multiply by d and check it outcome is n.
Exactly. So like we first have to handle the special case that the bottom character, then we check that d is 0 indeed, and otherwise we multiply by our output y by d and check this n. And actually here we don't really need a certificate. So then you may wonder, do we actually need a certificate? Is it actually required? And well, the answer is yes. And we will see this with a second example, slightly more advanced example, and that is divisibility, where we will see that certificate comes in handy for checking. So again, or like here in this case, we want to check if an integer n is integer divisible by d. And let's say both n and d are now integers. Again, the precondition here is that d is not equal to 0. And the postcondition is that, well, if d is 0, then the output is bottom character. But and then we output true if n is divisible by d, and false otherwise. And now, well, our result is just true or false for like this bottom character. So what would be a good way to like, how can we now check that this output true or false is correct? What would be like a good certificate in this case to make like the check easy? Any ideas?
The number that's the divising.
Yeah, or like the quotient.
Yeah.
Exactly. We could give like the quotient as like the rational number there, and then check basically. Well, first we check the bottom character, a special case, and then we could check if this quotient times the divisor is equal to n, and then if this quotient is an integer, then it should be true, or like the output should be true, and otherwise false is the correct output. So this is like a simple example where it's like handy to have like a certificate, and then we will actually see later that, or like for like our decision problems where you just get the output true or false, it is generally always a good idea to have a certificate where you can see like the reasoning done by the solver, or have like more information to make the checking process easier for you. So now let's talk a bit about like certifying algorithms and what we want, like what performance goals we want to achieve for them. Like we could have like the checker could run in any time or whatever, but actually we have some nice results that guarantee us that give us performance guarantees for the checking and the certificate and the size of the certificate. And so let us first make two restrictions or like assumptions that are like, well, generally true, at least for the algorithms that we consider. And the first one is that the precondition, we assume that to be satisfied always. So we don't need to check for the precondition. We can do this basically by having a separate program in front of it that checks it, or like enforce that precondition by a type system. And we will see that, well, these combinatorial optimization problems, they're so general, you can easily enforce that the precondition is satisfied. And second one, well, we want to have a correct algorithm and a deterministic algorithm that we consider. And then actually by a result from McConnell et al., we know that for such algorithms that have these conditions satisfied, there exists a certifying algorithm that has the same asymptotic running time as an algorithm that satisfies these conditions. So actually what this gives us as goals to shoot for our certifying algorithm is that everything should be scaling linearly in the running time of the original non-certifying algorithm. So this means specifically that the certification should only add like a small constant factor overhead. So it should be like the certifying algorithm should only be like a constant factor slower than like the non-certifying algorithm. And preferably that should be at most like 10% slower. Then the certificate, it also scales linearly at the running time of like because like the running time of the certifying algorithm scales linearly. The certificate size also scales linearly because we could not print more because then also printing would increase the running time of our algorithm. And also what we also can, another result that we have, or like what we have as a guarantee or like a goal to shoot for, is that the checking should also scale linearly. And here we are a bit more relaxed and we say, okay, we give the checker 10 times more time than the certifying algorithm has, because it might have to do more work to really make sure that the output is correct. So these are the goals. And so how do we do now? Certifying combinatorial optimization. And well, first we have some challenges, and that's what I told you about, that like they have all these different optimization problem, or like these combinatorial problems. Like you can ask, like we have this objective function and the set of feasible solutions. And then we can ask like different things about it. We can ask if there is a solution satisfiability. We can ask like what optimal solution is, optimization problem, enumeration, or counting. And then we also have a lot of different paradigms that look very differently. Like we have this in solving, there is no objective actually. So and we have these clauses as constraints. In integer programming, then well, there we have an objective and we have inequalities as constraints. And then we have even constraint programming, where the constraints can be very arbitrary. So how can we on Earth design a certification system for all of these different things and for all of these different paradigms and different results and so on? And so this will be this I will show you in the rest of this talk. And so before we get to this, let me just talk about some preliminaries. And as I told you before, we will we will encode things as pseudo-Boolean optimization problems. So here are some preliminaries for pseudo-Boolean optimization. So our variables are Boolean variables. So they have domain 0 and 1, where we associate 0 with false and 1 with true. And so we can define a literal to be a variable itself, or its negation x bar, and the negation is just 1 minus x. And then a pseudo-Boolean constraint, that's an integer linear inequality over the literals, like this one here. And sometimes it's also helpful to think about equality constraints. Like here we just have inequalities, but equalities, that's just two inequalities, like greater equal and less equal. And then a clause, you saw that earlier with the SAT solving that I showed you. Like a clause is either a disjunction of literals or at least one constraint where all coefficients are 1. So a clause is also just a Boolean constraint. So how do our certificates now look like? And well, the first thing we note is that the certificate looks different depending on the results that we get out of the combinatorial optimization solver. So for example, for satisfiability, like if the solver says that there is a feasible solution, then we could just give this feasible solution as a certificate, and then the checker checks that with this solution all the constraints are satisfied. But then for unsatisfiability, then, well, we actually have to prove somehow that there is no feasible solution, or there is no solution for the constraints. Again, for optimality, then, like when we want to give bounds, upper bounds and lower bounds on the optimal value, then the upper bound, like if we consider minimization problem, the upper bound is also just giving a solution that is at least as good as the upper bound that we claim. And, but then for the lower bound, there we actually have to prove that our constraints do not admit an objective value that is smaller than the lower bound. And then our result could be a reformulation of a problem. Maybe we don't actually solve the problem, but we just massage it, we do some pre-processing, and we return another problem. Then we want to guarantee that like this problem has the same optimal value as the original input problem. And so we again have here to prove that the optimal value is preserved. And so there's like these hard cases where we have to prove something. And there, well, let's just look at the first case. This maybe the easiest case is the unsatisfiability. How can we prove unsatisfiability? And well, there we can look at theory, and there is this field of proof complexity that gives us a nice framework of showing unsatisfiability, because there are these refutation proof systems for proving unsatisfiability of like a set of constraints. And so specifically, there's this sequential proof systems, refutation proof systems, where we have a set of rules, and using these rules, we derive new constraints from our previous constraints. And then the idea is that we want to derive a contradiction, and this showing that deriving this contradiction shows that we are unsatisfiable. And so a proof system has the following 3 conditions that it has to satisfy. First, it has to be sound. So if we can show unsatisfiability in this proof system, then the actual problem has to be unsatisfiable to start with. Then completeness, that if a problem is unsatisfiable, then there's also proof of it, which is quite useful for us, because then no matter what the optimization problem is, or like we always know that if this proof system is complete, then we have a proof to show unsatisfiability. And lastly, we have efficient and checkable. And here, this basically says that each rule should be checkable in polynomial time. And when we think about this more, then this, for our conditions that we want to have everything scales linearly and so on, like this actually polynomial time is not like restrictive enough for us. We more often shooting for that each rule is checkable in like the linear time, or even better, or even less. So this is actually now gives us a proof system, like a way to prove unsatisfiability. And the constraints that we will use for our proof system is, of course, the Lund constraints. But then what about other results? Like what if about proving a lower bound? And well, before we had that, well, we want to show contradiction, to show unsatisfiability. But when we could also do it is that we show that the objective is at least the lower bound. And this basically guarantees us that the lower bound, or that this LB value is a lower bound on the objective. And so our proof system has to guarantee that the lower bound does not change, or that the lower bound derived at any point is also a lower bound on the input problem. And secondly, if you want to have a proof of reformulations, then the way to establish this is to derive the constraints in the reformulated problem, delete all the constraints in the original problem, and then show that the objective can be changed from the original problem to the reformulated objective. And so for this to work, the proof has to guarantee that, like, in each step, we do not change the optimal value. So the optimal value is preserved. So we have like actually here like stronger guarantees on what the proof system like, or what the proof system should have like for it to be sound. And so now, what is this proof system that we look at, or how does the proof system work? And so again, we can take inspiration from proof complexity, and we have pseudo-Boolean constraints, and there is this cutting planes proof system which works with pseudo-Boolean constraints that we work with. And so the cutting planes proof system has the following rules. So first, we have a literal axiom that we can introduce at any point. Basically, the literal is greater than or equal to 0, and this just says that variables are between 0 and 1. Then addition, so we can add two constraints together where we cancel opposing literals by using that not x is 1 minus x. Then multiplication, we can multiply a constraint by an integer. Then saturation, this basically says that if a coefficient is larger than the right-hand side, then we know that like anything larger than the right-hand side doesn't help us with satisfying the constraint more. So we can basically just clip the coefficient to the right-hand side. So the coefficient after saturation is the minimum of the coefficient and the right-hand side. And then finally, we have division. And so we can divide the constraint by an integer. And this divides all of the coefficients and the right-hand side. And then we can note that, well, all our coefficients and variables, they are integers. So all the terms are integers. And the sum of integers is an integer. So our left-hand side is an integer, so we can with a lot of generality, round up the right-hand side. And this case would be 3. So as an example of how cutting planes works, like let us derive this constraint from, like starting with this optimization problem, we want to derive this constraint. And well, we can do this as shown here. So first we introduce a literal axiom for not x2. Then we multiply it by 2. Then we add this to the constraint 42. This cancels out the variable x2. So we have here 1 minus x2 and x2. This leaves behind a constant 2 on the left-hand side, which we move to the right-hand side. So our right-hand side becomes 1. And then we just divide by 3. And because we round up the right-hand side, this becomes 1. And then there's this nice thing about cutting planes, especially with this division rule, that it's implicationally complete. So any constraint that we can derive by cutting planes does not change the set of solutions, or like any constraint that does not change the set of solutions can be derived by cutting planes. So now we have a way to derive constraints, but where the set of solutions is preserved. But sometimes we want to change the set of solutions to like do stronger reasoning. So you want to sometimes add or remove solutions, or even introduce new variables. And for this, we have the strengthening rules. And there the idea is, or like for like the first strengthening rule that we have, like the general problem with like removing or adding solutions or constraints that add remove solutions is that, well, you're running into danger that you could add a constraint that removes an optimal solution. And you could remove all optimal solutions, and then suddenly like you don't preserve your optimal value. So you have to ensure that there exists, like after adding this constraint, the new constraint, there exists still at least one optimal solution to the formula, to the original formula that you started with, that also satisfies this added constraint. And the way we do this, or like how this is done, is by giving like a substitution that repairs every falsified, or every solution that is falsified by this added constraint is repaired to a solution that is also satisfied by this added constraint. So by the formula and the added constraint. Yes. So this is like the one of the two strengthening rules, and the second strengthening rule that we have is this dominance-based strengthening. And there, the idea is very similar, that we want to ensure that there exists at least one optimal solution that satisfies the formula, that also satisfies the added constraint. But here we allow that this repairing step can be applied multiple times. So in this redundant-based strengthening, we only have one shot to like basically one application of the substitution to repair. This is the falsified solution. Whereas here we can apply the substitution multiple times, and at some point we are guaranteed that this solution, this repaired solution, satisfies the formula and the added constraint. And this is very useful for symmetry breaking. So to see how this redundance-based strengthening rule works, here's a small example with some high-level intuition on why this works. So let us consider this problem, and we want to derive not x3 greater equal 1. And we can do this using the substitution, and as x3 maps to 0. So adding this constraint basically removes all solutions where x3 would be 1, because this only allows x3 to be 0. And then what the substitution basically says is that, well, with lots of generality, any solution where x3 maps to 1, you can set x3 to 0. And why can we do this? Why is this like valid? Well, x3 does not appear in our objective, so setting x3 to 0 doesn't make our objective worse. So we are at least having at least good solution, like qualitatively with respect to the objective. And then, well, setting x3 to 0, like for this constraint 42, it only makes things better because it satisfies constraint 42 even more. And then the new constraint, well, that's also satisfied by x3 being 0. So without loss of generality, setting x3 to 0, it's a good idea. Then, well, we can add constraints now, but what about removing them? Deletion. And, well, note here that deleting constraints arbitrarily, well, that's unsound, because then we could just remove all constraints and have an optimal value that is better than like anything, like just claim the least value without any objective and without any constraints. So this definitely doesn't work. And also what's actually possible is that with this dominance-based strengthening rule, it's even possible to remove all solutions by deleting or reducing this deletion rule. So you can turn a satisfiable problem that has solutions by deletion and dominance-based strengthening into a problem without any solutions, an unsatisfiable problem. So we definitely need to restrict deletions. And the way to do this is that, well, first, and to make things as easy as possible, we first partition our set into a core set and a derived set, where the core set, for this set of constraints, we have strong guarantees. And these guarantees are basically saying that the optimal value with respect to the core set, so having the core set as constraints and our objective function, that's the same optimal value as the input problem. And then derived sets, well, all our constraints just end up there. And so we don't have any guarantees on a derived set, except that we can extend a solution from the core set to a solution to the derived set. But then we can remove constraints at any point from the derived set to the core set. So basically, by moving it from the derived to the core, we are guaranteeing stronger things for it. And then, well, the deletion we can do is that we can always delete from a derived constraint because there we don't have any guarantees. But then for core constraints, there we have strong guarantees. So we have to ensure that the deletion does not change our optimal value, as this is our guarantee. And this we can do by using this redundant space strengthening rule that I showed you before. So by showing that we can rederive this constraint by redundant space strengthening, and redundant space strengthening preserves the optimal value, we can show that we can delete this constraint. So as an example, let us consider here this constraint 42 to be a core constraint, and we want to delete this constraint 42. And for this deletion, we don't need a substitution. So everything, or the check that we have to do is just saying that it's just checking that the deleting this constraint 42 does not change the set of solutions that we have. So how can we see this? And well, basically what we can see is that our remaining constraint after deletion is not x3 greater than 1. That forces x3 to be 0. And x3 being 0, well, that actually satisfies this constraint 42. And so, because this constraint 42 is satisfied, it doesn't have any restrictions, or it doesn't restrict x1 and x2. So x1 and x2 can take any value. And so can, also on the right-hand side, after deletion, x1 and x2 can take any value. So the set of solutions is unchanged. So now I talked a bit, this is like, we can add constraints, we can delete constraints, but what about the objective? And so finally, we can change the objective with the objective update rule. And that allows us to change the objective from an old objective to a new objective, basically if we have equality between them. So if in our constraints, we have this equality, which, if you remember the preliminaries, this is just two inequalities, then we can change the objective. And an important restriction here is that, well, we can only do this, we can only, both these constraints, like the greater equal and less equal, or the old and the new objective, that they are equal, these both constraints have to be in the core set. And because otherwise, there's one direction, that the old objective is less equal to the new objective. If this would be in the derived set, then it would be even possible to introduce solutions that are better than optimal. So it's similar to deletions. We have to restrict from which sets we derive these conditions. And then, well, I'm thinking about like how to specify this objective change. There are two ways we can do it. And the first like simple way is that, well, we just specify the new objective by just writing down the new objective. And this is good if the new objective is small, because, well, then we don't and we change a lot. So then writing down this new objective doesn't take up a lot of space. Otherwise, there's also the possibility to just write down the difference between the new objective and the old objective. And this is good if like we just change like one term in the objective, for example. So as an example, for changing the objective, let's just consider this optimization problem. And this constraint is 1. When we look at it and moving the 2x3 to the right-hand side, we can see that together with constraint 1, where we also move 2x3 to the right-hand side, we see that they are both together enforcing an equality. So they are both together saying that 3 not x2 plus 2x3 plus is equal to 2x3 plus 1. So we're having this equality. And using this equality, we can basically do a substitution of our objective, changing our objective to the one on the right-hand side. And then to specify the objective change, well, one can either just state the new objective, that is 2x1 plus 2x3 plus 1, or we specify the difference. And the difference in this case would be 2x3 plus 1 minus 3x, not x2. And so the difference is basically just stating the things, like the terms that are added to the new objective minus the terms that are removed from the old objective. And then if we add this difference to the old objective, we get the new objective. So, and this is basically all that is to know, and all how we manipulate constraints, optimization problems, like how the proof system works, how we can prove unsatisfiability, we can prove lower bounds, and we can prove problem accumulations. So with that, we can get to the contributions of my that will be included in my thesis, my PhD thesis. And so the first paper that will be included is about translations from pseudo-Boolean from pseudo-Boolean constraints to CNF, and using that for pseudo-Boolean solving. So there are these solvers that encode pseudo-Boolean constraints into conjunctive normal form. So there are all the constraints are just clauses. And the thing is that there are a lot of different encodings to do this, different ways to like write or like have these pseudo-Boolean constraints encoded into CNF. But the good thing is, and that what we observed is that they have like a very similar principle, and that is that they construct a circuit computing like the constraint and then encoding the circuit into CNF. And so the idea is that in this paper we provide a framework to make these encodings certifying, and with that, using that, we provide an end-to-end certification for CNF-based pseudo-Boolean decision solvers. So these solvers, they take a pseudo-Boolean problem, then encode it to CNF, and then just run a subsolver that solves this CNF problem, and then gives us the results satisfiable, unsatisfiable. And then by just concatenating the proof from our encoding and the proof from the subsolver, we get together one proof that certifies the whole solving process, and we get the guarantee that the problem is solved correctly, that the output for this problem is correct. Then the second paper is about Maxat solving. So in Maxat, we have a pseudo-Boolean optimization problem. So we have an objective now, but our constraints are still all clauses. So we still have clauses, and these at least one constraint. And then this co-guided solving, that's a very successful lower bounding approach. So we are improving our lower bound more and more until we get to our optimal solution, or optimal value. And in this paper, we provided certification for a state-of-the-art co-guided algorithm, and applied this to Maxat. We also provided certification for state-of-the-art pre-processing and additional techniques that are used on co-guided solvers. And this enabled, and through this, we were able to discover a bug in the state-of-the-art Maxat solver that uses this, that uses co-guided search. And we were only able to discover this bug because of certification. With just testing, we would not have been able to discover the bug, because the result was actually correct, but the reasoning how this result was obtained was incorrect. And we later found an example to actually gets the solver to produce a wrong result. And we would not have been able to find this without certification. And the idea here for this core-guided search is that, well, we have that the solver it changes the objective step by step, basically by adding the lower bound inside the objective. And so we maintain that the original objective that we started with is at most the reformulated objective. And so basically any lower bound on the reformulated objective that we get at the end is also lower bound on the original objective through this constraint that we maintain. In the third paper, the third paper is about solution improving maxat solving. So we again have the maxat problem. And in this case, we're doing solution improving search. So finding better and better solutions. So this is an upper bounding approach. And this idea uses these pseudo-Boolean to CNF encodings from the first paper. But then what it uses these encodings in a very advanced way, that it does like a lot of without lots of generality reasoning using these encodings. And in this paper, we were able then to provide certifications for like state-of-the-art solution improving maxat solver. But this required a lot of like new ideas. So this one idea that we introduced in this paper was the idea of shadow circuits, where we copy parts of the formula to have like a cleaner version of the formula, perform our reasoning on it, and then copy the results back to the original formula. Just to separate this like with this advanced without lots of generality reasoning better from like the rest of the problem. And to do this, we required to add this new strengthening to core mode, which separates this reasoning without lots of generality, which is the strengthening reasoning, and the implicational reasoning done with coming planes. Then another paper, paper 4, is about certifying mixed integer pre-solving. So this is a preprocessing technique or preprocessor. So most solvers don't solve a problem directly, but instead they give the problem first to a pre-solver and then or preprocessor, and then which massages the problem and makes it easier to solve for the main solving loop. And well, there exists already certification for like mixed integer programming solvers, at least in a limited form for like some techniques. But it's not possible to certify the reasoning done in this pre-solving with these certification techniques. And we wanted to re-show in this paper that it's possible to do certification for the pre-solving techniques, at least for the ones that are applied to 0-1 integer linear programs, and which should be like which is a first step towards establishing a certification system for general pre-solving, for mixed integer pre-solving in general. And in this paper, we actually introduced this objective update rule, which, well, one case, it's like it feels very natural because the pre-solver, it changes the objective. So there should be also a rule to do this in the proof system. But also it became necessary to do this because the strengthening, like the substitutions that we give for strengthening, they depend on the objective. And so without changing the objective, it became impossible to do to give the substitutions required for the strengthening. Before I get to the next paper, let me talk a bit about formula verification and trusting the checker. So before we had now this build, this picture, and that's, well, we have our problem, our tool, this gives a result, and then we have our checker. But can we really trust that the verification result of the checker is correct? Like, do you really trust that I implement the correct checker? You should not. I wouldn't. So this checker that I implemented, well, it's actually unverified. We don't know if this result that returns or this verification result is correct. And so it would be good to have a formally verified checker. And so we replace this verified with unverified with verified. However, the issue is that our proof system contains a lot of syntactic sugar, which I will talk about a bit in the second part. And this, for these syntactic sugar rules, it is very hard to do efficient formally verified checking. And so the idea of what we do and what a lot of other papers work before us already also did when doing formally verified proof checking is to use this unverified checker as an elaborator. So we have this proof that has the syntactic sugar, and then we have this elaborator which removes the syntactic sugar and translates it to easier rules that can be checked efficiently by a formally verified tool. And so we have the simpler elaborated proof now, and this can then actually be fed into a verified checker that for example, we verified it with Isabel, and then you get a verified guarantee about the correctness of the result, or you get a rejection. So that result that the verified checker outputs, you can really trust that. And so in the paper 5, this was the first time we used this. So there was already certification for subgraph solving, and the checker there was unverified, and it might accept or say that incorrect proofs are correct. And we, in this paper, added elaboration for the syntactic sugar to our proof checker RPB. We formally verified encodings of subgraph problems into pseudo-Boolean problems. We also formally verified the checking of RPB certificates in this proof checker HPB. And together with this, we get end-to-end guarantees that, like, because we have a formally verified encoding, we can start from like the original encoding of the problem to the result. We know that we have a guarantee that this is correct, or that the result returned by the formally verified checker is correct. And the way we designed it to have like this encoding, and then the checker only works with this RPB format in the backend, this makes the checker very extensible. So the backend, that can just be reused, like the checking of the RPB format, because that just talks about pseudo-Boolean problem or pseudo-Boolean constraints. Whereas like we have this front end, which then actually takes care of translating our original problem into a pseudo-Boolean problem. And then translates also the result back into the input problem domain. In paper 6, we are again talking about, talking about Maxat problem. And here we introduced certification for standalone problem reformulations. So if you just want to, if the preprocessing is not part of like a solving directly, but you want to like preprocess a formula and then give it to like 10 different solvers, you might just want to know if the preprocessing itself is correct or correctly done. And so this paper, we provide this for a Maxat preprocessor. We provide certification for all known Maxat preprocessing techniques. And we, again, through the formally verified framework that we did, we have first the encoding from the Maxat problem or from our input problem into PP, into pseudo-Boolean. So we can guarantee that the input problem is or has the same optimal value as the output problem with respect to the input problem, like to the original problem domain. Then in the paper 7, there we looked at symmetry breaking, and well, the current state of the art symmetry breaking that was before this paper scales quadratically in the size of the symmetry or like the running time of the solver. And as we've seen before, we want to have everything just linear. So this is not good. And the main bottleneck here was the encoding of an order. So for the symmetry breaking, we want to get the minimal solution with respect to like an order. Like we want to have already define the canonical solution to be like the minimum with respect to an order. And then encoding this order was taking like quadratic size. And in a paper that will be presented in 2 weeks at AAAI, we added to our certification system that it is possible to introduce additional variables, auxiliary variables to define these orders. So then the certification, everything stays linear, because like in the old encoding, we had these coefficients which were size, which scaled linearly in the size of like of n. And so if we have n of these coefficients, so then we're having n squared size in the encoding. But with the new encoding, we can use these auxiliary variables, which basically just say that when we're comparing to binary strings, that the strings are equal up to position s or at position I, where I is the index of this s variable. And in a third paper that is still work in progress, which I plan to include in my thesis, we looked at trimming. And so the idea of trimming is that, well, you're just interested in the final conclusion of your certificate. So, for example, the contradiction in uncycled specifiability proof. And so there might be additional reasoning that is not required. And so you might just start from this final like constraint that is required to witness like this certificate, the result, and go backwards from it and check like its antecedents, and only check the parts of the proof that are actually required for showing the result. And yeah, and trimming basically means that we remove all unnecessary things, and backwards checking is starting from like the final, from the constraint, certifying our result, going backwards and checking on the antecedents. And so we provide trimming and backwards checking, or we plan to provide this in this paper for various B certificates, and also provide trimming for advanced strengthening rules. So, and this then can be used to get small certificates, which can be an advantage for storing these certificates for longer, and also to provide faster checking, because then you just have a smaller certificate size. And additionally, it can also be useful for understanding which constraints and which reasoning in the proof was actually useful to derive the result. So some further publications that I am not planning to include in the thesis are here. So there is one paper about certification for systems that reason with states and transitions. So you can think about it as like dynamic programming algorithms or like decision diagrams. So this is like a very general approach where we have where we can represent like a state as some pseudo-Boolean constraints. So we're thinking about a knapsack problem, for example. There you have like your items that you took. So your remaining capacity is like one constraint, and then your you have like a and then you have another constraint on like a profit that you can get with this capacity. And so this is like a very wide range of algorithms, and just this captures a lot of like different algorithms that we capture with this paper. And then in this paper, in this last paper here, there we look at pseudo-Boolean optimization, and we provide certification for pseudo-Boolean solvers that actually satisfies these conditions that we would like to have, that we that the overhead for solving or for, like on the solver for certification is like within 10%, and also that the checking of the certificate is fast enough, so it's within 10 times the solving time. Some other papers that we currently work on, but might not be included in the thesis, is that we work on certifying graph coloring solvers, and also we work on certifying enumeration solvers. That's just side note. So to conclude, certifying algorithms is a great idea. You should do it. It gives you guarantees about the correctness of the results of your solver, of your algorithm. And VeryDB is a multi-purpose certification system that can be used for decision problems, optimization problems, problem reformulations, and can be applied to a lot of different problem paradigms. So pseudo-Boolean optimization, maxat, pre-solving, at least subgraph problems, and dynamic programming. And with KPB, we provide also an extensible, formally verified framework to get formally verified guarantees on correctness of the results. Additionally, like work that I've related work that has worked with VeryDB has also shown that the certification system can be used to certify multi-object optimization. So iterating like the Pareto front of like multi-object problem. And then VeryDB can additionally also be used for certifying sub-solving, constraint programming, and classical planning. So as future work, well, it would be great to bring certification with like this unified system to more and more paradigms. Then it would be great to like to extend the system to other types of results. So enumeration is one, but also counting of solutions. Then we currently only allow Boolean variables and integer coefficients, but it might or should be possible to extend this to integer variables and allow also rational coefficients. And there has been preliminary work on that, which has been purely theoretical. And finally, it would also be good to integrate this weak substitution redundancy rule from Evola Pato in our proof system. So for improving the checker, of course, it would be great to improve the performance of it. Then it would be interesting to figure out how to do parallel and distributed proof checking. It might be interesting to have an API for interfacing with the checker directly, so that while running the solver, you can directly get feedback, or the solver can directly get feedback if it's doing the right things. There would be an interactive mode would be interesting, that when you have a wrong proof, then you're thrown into like an interactive session where you can figure out how to fix the proof. And currently, like our checker only supports like one mode, and what might be interesting, depending on what your goal is, to have like a more permissive mode if you're just interested in the correctness of the result, so that the checker actually tries to like figure out like how to fix the proof if the proof is slightly wrong. Or you want to have a strict mode where like the solver complains every small thing that you do wrong. And so with that, that's all for the first part. And are there any questions?
Thanks, Andy. So questions from the audience or from the virtual audience? And then as Andy mentioned, we'll take a break and then continue, but it's time for some questions now. Let's see. Yes.
Is it okay if I?
Sure, go ahead.
There's nothing urgent there. Well, thank you for a very detailed presentation, actually. And the questions that I have are a little bit more on the meta level, yes, as you might figure. So, given that you probably do not have that much time when you will present during the PhD defense, how do you think you would frame this? Would you just go in with the contributions, with paper, and what would then be your kind of core thing, your core question that you would want to talk about? I mean, I've just checked against your licentiate,
Mhm.
which was published very recently.
Yes.
So in terms of numbers of papers, there are 2 more
Mhm.
that you would want to include now. But none of the papers that are included has you as first author. And I don't know if that's in your field is
Yeah.
sort of
We do alphabetic order.
Sorry?
We do alphabetic order usually,
Alphabetic,
so
okay, yeah.
yeah, so
then-
that's
then it's all good.
my last name is not that unfortunate.
No, that's
No, but the main confusion, or what I would say, is that like we have this general unified framework that can be applied to as many like different solvers and paradigms and whatever is possible. So what's like, especially with the selection, what I included the papers, there it's always been developments that made progress in the actual format of the proof system.
Mm.
So not too much about applying the proof system, but like adding things where we notice like coming into like a new area, noticing, okay, these are things that we are lacking in this proof system, and this and yeah, this is I think the main thing.
Do you plan, Jakob, maybe to have the opponent present?
We usually do the opponent. The opponent to the resolution.
The entire, like the classic? Yeah, okay. No, then it's, I mean, then it's not even your problem.
Yeah.
to find the entry. Because I mean, we've gone here from, I've seen all variations. So,
Yeah.
Okay, very nice. Yeah, then I actually, thank you, and have a good continued discussion.
Yes, thank you.
There is a question in the chat.
Yes.
Is there any other reason we want linear checkers over, say, quadratic ones, other than quadratic is a better runtime than linear? So why did you put linear as a benchmark?
Because we can achieve it always. Like we have a theorem that says we can achieve linear, so why should we do quadratic? Why should we be happy with quadratic if we can do it linear? Like we know it.
In that theorem, by the way,
Yes.
that you can achieve good certifying algorithms, what's the constraint on how simple these algorithms should be? Like, why can you not take the correct algorithm and just run it and see if they output the same answer?
Well, that's actually almost a proof, because
Okay, yeah.
you have a correct algorithm,
Yeah.
and for it to be correct, there's a proof for it. So you can like state in the formal system, you can formalize the proof. And then with that, you can, like a checker basically, it has this formally, like it has the proof of the formal correctness, and then the certificate is just a trace of the computation.
Yeah.
And then you check against like this formally verified, if like the trace satisfies or like is correct for this formalization of the algorithm. Yeah, so yes.
Yeah, actually about this theorem. So does it really say something about like there exists a proof system in which you can formalize these proofs, or is it not that like?
No, it's not that specific. It's more general, and it's more high level in the sense that like because of there is a correctness, you should be able like to formalize the correctness, otherwise it would not be correct. So, yeah.
But even without that, like if you just run the original algorithm outputting an empty certificate, and then your checker is the same algorithm solving the problem from scratch and seeing if the answers match.
Yes.
Would that also satisfy the theorem?
That would satisfy the theorem in itself, yes.
Yeah.
All right.
But what you actually get is something that is
Yeah,
more...
exactly. But like doing this actually in practice, then this is the challenge. Like you can theoretically achieve this, that's what the theorem says, but actually doing this in practice, then it's like the challenge.
With something that is
With
more
no-
easily checkable than the original
Exactly,
algorithm.
and
But is there a
Take
theorem
away
stated
that
for problems that can be solved in polynomial time? Do they use this?
no.
No.
because like, well, if it runs in exponential or like exponential time, then well, the running time is exponential. Then you have exponential time to run your checker. So.
Any other questions? Otherwise, I think we'll take a break. So we're back after the break, and Andy will now continue with the second technical half, please.
Yes, exactly. I prepared some more presentation for a second half where we go into a bit more detail. So first we will go a bit more detail into the proof rules that I presented in the first part. Then I will give you an example of a certificate, how it looks like, and we will run why it's correct and so on. And I will actually show you running this example through the checker, which actually gets us to like the implementation of the checker. So there's one implement in software. And then I will talk a bit about elaboration and trimming. So how are the proof rules? How do they work? And first, let me flash you slides with a lot of text. This is basically the state maintained by the checker. Where like the first part, half is like more interesting for this part of the talk, and the second part is more like auxiliary things that are maintained that are important, but not so much for this talk. So like the checker, and we call this the configuration, the checker maintains like the core set, the right set that I told you. Then like, well, we have to maintain the current objective. And well, then there's this border, and this I will talk about in a few slides. But first, let's just take a step back and add implied constraints. And well, these are the constraints that do not change the set of solutions. So a constraint is implied by a set of constraints over F if both the set of constraints in F and F union, the new constraint, have the same set of solutions. And well, cutting planes is implication complete and so on. So we know that like if a constraint is implied, then it's derivable by cutting planes from this set F. And so what we write is that we write this F derives C to denote that the constraint C is derivable by cutting planes. And then for a set of constraints, then we write that, well, this set F prime is derivable from F if every constraint in it is derivable from F. And so then we have some more syntactic sugar for like the implicational rules. And this is basically to use or for using when we have some obvious implied constraint where we are too lazy or like it's too tedious to write down the cutting planes derivation. So the first thing is syntactic implication. And this is basically a cutting planes derivation that where we can derive a constraint from another constraint by adding literal axioms and saturation. Like just doing these two rules in arbitrary order, with arbitrary literals, we can derive these from C. And there, for this, I will show you later, we have an efficient check for this condition. Another condition, or easy to check thing, is reverse unit propagation. And this is basically a proof by contradiction, where we have our set of constraints F, and we know that the constraint D is implied by F if the set F union the negation of D, so we assume the negation, and if this necessarily leads to a conflict, which we do by this propagation procedure, if we necessarily know that like this is gives us a contradiction, then we know that the constraint D is implied. So it's basically just a proof by contradiction. Assume the negation, and then if it's a conflict, then it's implied. So this is about implied constraints. So then for strengthening constraints, let me first introduce you this order that I showed you on this first slide of this part. And well, the order, you can think about it as like somewhat as like an objective. So you're like sorting, or you're sorting different assignments. And so you have like the order should be reflexive and transitive. That's like important. And you're comparing assignments, not like full assignments, but only restricted to like a subset of variables. So you're only interested in like a subset of variables where you want to compare, is this assignment smaller than the other? And we have it reflexive and transitive. And then how do we actually realize that? And so an order is actually defined through pseudo-Boolean constraints. And so if the pseudo-Boolean constraints evaluate to true, then the order holds. So we're having these two set of variables, u and v, which is like, you can think about this as like one assignment and our assignment. And then this formula, these constraints are satisfied if and only if like the one assignment is larger than the other. And well, I told you that we have introduced like this auxiliary variables recently, which we presented at AAAI. And these are these variables A. And for this, we are giving an auxiliary specification, which I call A here, which basically defines these variables. But in most cases, like you can basically ignore this A, like this A, the set of constraints A and this variable A. These you can trust they are set up correctly, and like the proof system will take care that like everything goes well with them. So in most cases, you can just ignore it, and also this auxiliary variables are not necessary. So you can just it can also define an order just without any auxiliary variables and auxiliary constraints. And then, well, we have the conditions that the order is reflexive and transitive. And what this means basically is that from like just our auxiliary, like from nothing, like an empty formula, we can derive that that u is greater equal u, basically. And then for transitive, it's similar. So u is greater equal v, and v greater equal w. So then we have to be able to derive that u is also greater equal w. And so this is basically just standard cutting planes derivation that we're doing here to establish that the order is transitive and reflexive. And then so if we have an assignment, then we just apply a restriction. So basically we have an assignment alpha and beta here, for example, and alpha is greater equal beta if these constraints are satisfied. The restriction, where this means here, this restriction that for the variables, for the set variables, we use the value in alpha, and here we use the value in beta. 1 second time. Yes, and so with this order, we can now really formally give you the definition of redundant space strengthening. And remember again here that the idea was that we want to repair a solution alpha that is satisfied by our core and derived constraints, but not by our new constraint C that we had. And we want to repair this in one step. And to show this, well, we give like this substitution, which we repair, has to be given explicitly. And the substitution that basically is just mapping from variables to 0, 1 literals. And then we have to show for C to be derivable, we have to show that this derivation holds. And what this that this derivation holds. And this derivation has to be efficiently checkable. And efficiently checkable means it's either obvious to the proof checker that it's derivable by either the syntactic sugar rules that I showed you, or you have to give an explicit cutting planes proof for this derivation. And so what this derivation says is that, well, we have this precondition here that like C and that any solution satisfying our core and derived set, but not our added constraint. Then after fixing the solution with our substitution omega, we have that it satisfies the core set, derived set, and our added constraints. So that our added constraints. And additionally, we also have that with this fix, the new solution, the optimal, the objective value is at least as good, or is also more like, is at least as good as like the objective value without this fix. And also our order doesn't get larger. So at least as good with respect to our order. So then we know that like any solution that is falsified by C, it can be fixed up or is patched up by basically concatenating, resulting in a new solution where we satisfy all the constraints and that is at least as good with respect to order and objective. And then for dominance-based strengthening, there we are allowed to use multiple steps to patch up or to repair the solution. And so it looks very similar that we are required to give a substitution explicitly. And this time we can introduce a constraint if these conditions are satisfied. And what they say is that, well, again, on the left-hand side, we have that core derived are satisfied, but our added constraint is not satisfied. And then the only condition we have on the constraints is that the core constraints are satisfied. So why don't we have a derived set? And that comes from like this guarantee that I mentioned earlier, that like the derived set, that for any solution to the core set, we can extend it to a solution satisfying the derived set as well. And then additionally, our objective function does not get worse. But then we also have that our order does not get worse. So as before, but then we have also this condition down here. And what this condition says, like this time, we have the substitution on the other side. So this means that our, when we can show that that the order with like with the substitution on the left-hand side, so with the substitution is greater equal than without substitution. That leads to conflict. Basically means that that with the substitution we cannot be at least, or the order is not at least as bad, so to say. So it's greater, not greater equal. So especially what this says and what case this excludes is that because we've shown that the order is improving, so it's less equal. So new with substitution, we are at least improving. We have at least, but then we don't have equality. So we're strictly improving. So our order is strictly improving. And yes, so with the substitution, our order is strictly improving. And so if our substituted, like if our repaired solution does not satisfy this added constraint, then we're good. But if it doesn't satisfy, then we just apply the substitution again. And for this, again, we know that like we get now a solution that satisfies the core constraints, the derived constraints, is at least as good with respect to the objective, and is strictly improving with respect to the order. So it's always like if we apply this again and again and again, then we're always improving strictly with respect to the order. But this cannot go on forever because we don't have like, we only have like a finite amount of like solutions or like assignments. So at some point it has to end and we have to get a solution that satisfies our derived constraint. And so to give a bit of intuition, between the difference of like this redundance-based strengthening and dominance-based strengthening. Let us consider an example of how these substitutions act. So we want to derive the constraint not x plus not y greater equal to. And with redundance-based strengthening, we can do this with the substitution. It maps x to 0 and y to 0. And so before, like we had no constraints, for example, and so before basically any of these 4 solutions here in this unit square were possible. So x can take any value, y can take any value, but after when we add this constraint, only 0, 0 is a valid solution. And then this substitution basically maps all our solutions to 0. So it has to be one step, map all falsified solutions that were valid before to a solution satisfying the added constraint. However, in dominance-based strengthening, we could have a substitution that says something like x maps to 0 and y maps to x. And then what this looks like is that, well, we still have that one step. It maps back to a valid solution, but we can also be in the case, for example, here, that the solution 1, 1 maps to 0, 1 and then to 0, 0, because x becomes 0, but y becomes the previous value of x, which was 1 in the first step, and only in the second step we get to 0, 0. So the substitution can be applied multiple times to get to a feasible solution. So that's the strengthening rules. And then for deletion, well, we've seen that we can always delete the constraint from the derived set. And then for deleting constraint from the core set, there's actually 2 deletions that we have. I only mentioned one deletion before, but there are actually 2. And the first one is the one I mentioned before, that we have this check deletion, which gives us stronger guarantees. And this is similar to redundance-based strengthening. So we are requiring a substitution, and then we can delete the constraint if we can rederive it from the core set without this constraint that we delete. And again, this derivation should be efficiently checkable. So, and note here that this is exactly the same as redundance-based strengthening, except that, well, here we had core and derived set, but this time we have only the core set without the added constraint. And here, again, we only have the core set. And then it's the core set without the added constraint, union the added constraint. So it's basically the core set again. And then additionally, we also have unchecked deletion, where we can delete any constraint, also from the core set. But the important condition here is that the order is trivial, because otherwise, as I told you, with this dominance-based strengthening rule, you can turn a satisfiable problem into an unsatisfiable through deletion. And we also, through this unchecked deletion, we lose guarantees on the upper bound, so we can't claim anything about the upper bound anymore. And finally, the objective update, here a bit formalized. It's basically we can change the objective if we can derive from the core set these 2 constraints. So let us then look at an example of how to do a derivation and a certificate for solver. And so a proof, well, that always starts with this first line, which specifies the version of the proof format, in this case version 3.0, and then we load the input problem. And this is loaded from like a different file, and most often this is an OPP file, which is like the pseudo-Boolean, the standard pseudo-Boolean file for file format. So in OPP file, constraints look like this, where we use this tilde for negation, and we have this objective here, and this translates basically to this optimization problem in like written down. And then for our proof system work, we also assign IDs to every constraint, starting from ID 1. So this first constraint we load from the input problem becomes constraint 1. And so on. And then we can start with our certificate. And so maybe the first thing we notice about our problem here is that like the first two constraints, they're expressing that like x1 is equal to not x2 plus 3 plus 4. And so we can basically substitute x1 in the third constraint using this equality. And to do this, well, we can use this, we can use cutting planes, and to use cutting planes, we have this Paul rule. And this Paul rule is like that we write down the cutting planes derivation in reverse Polish notation. So you're first writing down the operands and then popping from the stack when you have like an operator. Like here, for example, this means that we take constraint 1 and constraint 3, and then add them together. So we add them together to derive constraint 4, and this is basically just how we do substitution. Then we want to remove the constraint 3, the old one, but that we move this constraint 4 that we just derived to the core set, and then do a deletion of constraint 3. And when we do a deletion, then we're saying that we delete the constraint with ID 3, and here without any witness. And we give an explicit subproof, so we have to give like a cutting planes proof or a cutting planes derivation, showing that we can delete this constraint. And this basically at the beginning, it adds this negation of the constraint. So we always had this core derived and then not C, when you remember back to the definition of redundance and deletion and so on. So you get the negation of the constraint we delete, which is x1 plus not x5 greater equal 2. And then, so we basically, what we just do is we add this constraint, this negation, like the previous constraint we just derived, together with the constraint 2, so the other direction of the substitution. And then we add this result to the constraint 4. And this gives us a contradiction, and this like gives us or this like shows the subproof. Or this ends the subproof, and we can delete. We have shown like all the derivations because we have derived the contradiction, and with contradiction we can derive anything basically. So this is substitution, and yeah, like here on the left you see exactly how this looks in the file. And so the proof is basically also just a file. Then we can do an objective update. Again, we can use this equality here in constraint 1 and 2. And this time we say that x1 plus x2 is equal to x3 plus x4 plus 1. And so, because like the two constraints are like encoding each direction of the equality. And so what we can just do is we claim this new objective. So obu is objective update. Then new means that we're specifying the new objective that should be replaced, or that we should be replaced objective with. And so this says that, well, x3 plus x4 plus 1 is the new objective. Then third step, well, we delete these substitution constraints. We don't delete them anymore. Basically, we can do this because they just, these two constraints, 1 and 2, they just define x1 plus, they just define the variable x1. So we can just delete them. And so first we delete this constraint 1. And to do this, we use the substitution that x1 maps to 1. And this time we don't need any explicit proof. Actually, everything is very simple to figure out, and so the checker can figure this out on itself. So this deletion, first it introduces the negation of the deleted constraint. Then the first constraint, like checking, going like through our like obligations, our conclusions that we want to get on the right-hand side of our derivation. We have the first constraint. And well, for the first constraint, we get that this constraint is actually under the substitution. So we're setting x1 to 1. We get constant 1 here, which moves to the right-hand side. We get this constraint here with greater or equal to. And well, this is actually implied by this constraint 4, like just by weakening away or like adding not x5 to this constraint. For the second constraint, well, there this is implied by the negate constraint, like negation of the deleted constraint. Again, just by weakening this variable x1 by adding x1 greater equal to 0. And then the constraint 4, well, the substitution does not affect it, so we have it on the left-hand side and right-hand side of like derivation. And then also the substitution does not affect the objective, so everything. So there we don't have any change. So that's this redundant based strengthening step is fine. A note here actually that if we didn't change the objective, then we would still have x1 in the objective. So we would have a condition here, but we don't have it anymore because we changed the objective. And then we delete the other direction of the constraint. And here we use that x1 is 0. And so the second constraint, it just turns trivial with this with the substitution. And then the substitution again does not does not change constraint 4, and it also does not change the objective. The next step, we do duality-based fixing, because like now we can look at our constraints and our objective, and we can see that x2 and x5, well, they can be fixed to 1, as this just satisfies the constraint more, and the objective, well, both kind of variables appear with coefficient 0 in the objective, so setting them to 1 doesn't make our objective worse. And again, for similar reasons, we can set x3 and x4 to 0, because that only helps us to satisfy this constraint. And well, they appear in the objective, but setting them to 0 is like the best case we can do. And well, we could now add like this fact that we say x2 greater equal 1, like this fixing, we could add constraints explicitly, and then add them to the objective and then delete things afterwards. But we can actually also directly use this fact that we can fix x2 to 1, x3 to 0, x4 to 0, and x5 to 1 as a substitution, and delete constraint 4 directly. Because then this just trivializes all the constraints and the objective that gets better. So we're now left with an objective and no constraints. And the objective has like a constant 1. So well, our optimal value should be 1, because we can set x3 and x4 to 0. And so what we now just have to do is do some bookkeeping. And so for witnessing that our lower bound is 1, well, any constraint certifies that. So we could just derive, like, for example, 0 greater equals 0 would be fine. And for the other bounds, well, we could give a solution setting x3 and x4 to 0. That satisfies all the constraints, and we're fine. And to do this, well, we can use this reverse unit propagation to add this constraint that 0 is greater equal 0. So this just adds this trivial constraint. And because it's trivial, the negation of a trivial constraint is a contradiction. So reverse unit propagation easily works. And then this solve rule, with that we log a solution. And so we say that x3 is 0 and x4 is 0 with this solve rule. And then we just have to conclude the proof, saying, well, we have this output rule at the end, which says like if we have like something or like a reformulated proof that we would like to output and where we want to have guarantees on, but we have a conclusion, like we know what the result is, so we just output this conclusion, and we say that we have an optimal value by saying that we have our bounds, where the lower bound is 1 and the upper bound is 1. And then we just say that we have this, or we give as a hint that we have this constraint 8, which we just derived here. So this becomes as ID8. That certifies us the lower bound. And then we have the proof. And so the whole proof looks like this. And then we can actually also look at this. So is this large enough on the?
I think it's okay.
So
You can make it slightly larger, maybe.
Slightly larger.
That's good.
That's good. So for example, then like here's a certificate basically that I just showed you that we just wrote together. And I added some comments like with this, like the lines starting with this percent sign. These are comments. And so you have these 5 steps that we did, and then we have this finalization at the end of the proof. And also just to show you the input file, that's like the input that I just showed you, this OPB file. And then we can use VeriPB and run this. First, we give like the input problem in this OPB file. And as the second, we give this the certificate. And then it says to us, verified the bounds, and the objective is between 1 and 1, which means it's 1. And we can actually also, what we do is we can have VeriPB like give us more information on like the steps that it did with this -t option, which gives us a trace of like the checking. And so it tells us like which constraints it introduced with which IDs. And here also the objective was updated at this line. And then for example, for objective update and also for deletions, it tells us like which proof goals we have, which are like the conclusions on the right-hand side. And then also how they are proven. Like it says then, okay, this is implied by a different constraint in the database, or the second proof goal that is like stated here. Well, that's trivial, so we don't have to prove anything. Yes, that's how VeriPB looks like and how you can use it. And so, and this gets us to like the checker directly. So immediately, so there's this VeriPB, which is like the reference implementation. It's written in Rust. It's available on GitLab, and it is link or following this QR code. And it's open source, and it is like the reference implementation for our proof format. It has to specialize data structures and algorithms for efficient checking. And so, for example, let me go through some like efficiency considerations. We have like for constraints, like the data structures, there we have a hard requirement that we have to support arbitrary integers for like coefficients at right-hand sides. But then the issue is that arbitrary precision arithmetic is relatively slow. And so the workaround is that we have different specialized data structures. So if we don't know that all coefficients are 1 and the right-hand side is 1, so we have a clause, then we just store the literals. So we don't store any coefficients on the right-hand side. For cardinality constraints, so if all coefficients are 1, then we just store the literals and the right-hand side. And then also for general pseudo-Boolean constraints, there we try to keep the integers as small as possible. So we have specialized data structures for like 64 bits constraints where all coefficients on the right side are represented with 64 bits and also with 128 bits. And this just improves like the performance significantly, because then if you're always staying within 64 bits of computation, then it makes no sense to use arbitrary precision, because it just slows you down. Then for RUP, or reverse unit propagation, let me just, if you like, definition or like some more an idea what reverse unit propagation does. So in reverse unit propagation, we keep track of a partial assignment, let's call it row, and that's initially empty. And then a constraint propagates a literal if this constraint would be falsified by the current assignment row and setting the literal to the opposite value. So basically, we are forced to take this because otherwise we're forced to take this we are forced to set this literal to this value, to true, because otherwise this constraint would be falsified. And then we would add this literal, or this propagation, setting this literal to true or to 1 to our partial assignment. And so if at some point a constraint inside this inside our set F union the negated constraint we want to derive is falsified by our partial assignment, then this constraint is implied. And so two things that we let me just first show you an example of how this works. So we have these 3 constraints, and when we look at the first constraint, then x has to be 1 because otherwise this constraint would be falsified. So x becomes 1. Then we look at the second constraint. Now x, not x, so that term, the first term in the second constraint becomes 0. So to set this, so if y would be set to 1, then this second constraint would be falsified. So y has to be false or 0. And now looking at the last constraint, we see that, the first term is 0, the second term is 0. So there is just not set greater or equal to. And our variables are between 0 and 1. So this can't be, so this third constraint is falsified and we have conflict. And so we take 2 inspirations to make this efficient. First, we use watch literal propagation, which is inspired from SAT solvers and pseudo-Boolean solvers, to not keep track of all the terms, when values change, to not look at a constraint every time variables assigned of this constraint, but only keep track of enough literals of this constraint to detect any propagation. And that's precisely when the sum of the watched terms, so the sum of the coefficients of the watched literals, is at least the right-hand side plus the largest coefficient in the constraint, because then we can detect any propagation. And another thing for optimization for performance is that it's trace saving, which is inspired by the DRED checker, so it's another proof format. And there we trace saving, basically we store propagations from previous propagations if the reasons are still valid. So if we have still the first 2 constraints, then we can keep these propagations also for these next propagations. However, if we delete this first constraint, then we have to delete all the propagations. The syntactic implication, here's the definition again. So anything that is derivable by adding literal axioms and saturation, that is syntactically implied. But with a loss of generality, we can note that we can just saturate. We only need to saturate once, and that's with that's when the right-hand side is the right-hand side of the constraint D that we want to derive. And that's because, by adding literal axioms and saturation, you can never increase your right-hand side. You only can, either you keep your right-hand side or you decrease it. And so the algorithm, basically what it does is that we just keep track of the new right-hand side after the necessary constellations. And just to briefly flash that to you, this is the algorithm. So you just have to go through the terms, or you keep track of your right-hand side that you get after all the necessary cancellations that you have to do, which is initialized to the right-hand side of C, and then you go through your terms in C and see if they have to be if they have to be cancelled out, and by how much. And just to briefly show you some performance figures. So these are some latest improvements from VerityB version 2 on the left-hand side, VerityB version 3. And this is on benchmarks from this MaxHut pre-processing paper, where the performance improved by almost 20 times. And this was mainly due to changing from a combination of Python and C++ in the implementation to pure Rust, and also having a bit more specialized algorithms with like the experience that we have now from designing a proof system. And so let me finish with talking a bit about elaboration and trimming. And so the goal for elaboration is that, well, we have this motivation that the syntactic sugar rules, they cannot be checked by formally verified checkers, especially this reverse unit propagation. And so we need to have a more easy certificate that the formally verified checker can handle. And so the idea is that, well, why don't we just do a certifying algorithm for our checker? So we make our checker certifying, and so it outputs a new proof of like the checking of the syntactic rules. And so the goal is basically to add enough details for the formally verified checker. Then the checker, the elaborate proof should still be a valid VerityB proof, so we can feed the same proof back over to our original checker. And hopefully it should be easier to check, so maybe the checking of the elaborated proof is easier. And so the basics of that is that, well, for the constraint IDs, they are different in the original proof and the elaborated proof, so we have to keep a mapping between them. Then for syntactic sugar rules, like we have to elaborate them, and there, well, for syntactic implication, we know that it's just adding literal axioms and saturations, so we write down the cutting plates derivation. And for reverse unit propagation, we just give the constraints that propagate and in which order, so that the verified checker doesn't have to perform search. For auto-proving, so this is like what we do when this checker says that like the conclusions are obvious for like redundant space strengthening, dominant space strengthening, and so on. This basically just uses syntactic implication and wraps, so we can use the same elaboration from like the syntactic sugar and translate this to explicit cutting plane proofs or explicit derivations. So for trimming, previously mentioning, we only want to check what's actually necessary to derive the conclusion. So we want to, anything auxiliary that we don't need for the conclusion should be removed. And so the approach to do this is we start from the constraint certifying our result, which for example is the empty constraint for an unsatisfiability proof. And we mark this. And then going backwards through the proof, when we encounter a marked constraint or marked step, then we mark all the steps that are needed to derive this step. So all the antecedents of it. And this we do going backwards through the proof. Anytime we encounter marked, we encounter its like dependencies. And then basically at the end, and we are at the beginning of the proof, all the marked steps are our trimmed proof. And the difficulties here are that when we have different rules, so for cutting planes that we directly know which constraints are the antecedents, but for reverse unit propagation, it's not so clear. And then also for strengthening, the conclusions depend on the current markings, like our current derived sets. It's a changing target. Like each time we check the conclusions or the current derived sets of the current mark. And so what we have is that with elaboration, we can, like what matters most is like this performance of the whole tool chain. And so it's not necessarily the best idea to elaborate more detail, because that will slow down your elaboration, and that in total could slow down your whole tool chain. So you just want, like more detail could make your verified checking faster, but it will increase the certificate size, which will slow down writing and reading the proof. And so you have to balance how much to elaborate. And still the formally verified checker needs to be somewhat sophisticated to handle, to not need every detail. And then for trimming, it's similar. That's a smaller certificate. Getting to a smaller certificate can take more time than trimming, and it might not pay off that immediately. However, if your sole goal is to have the smallest possible proof, then you might just want to spend a lot of time. So final conclusion. Well, it's difficult to design like a correct and efficient certification system, I would say. And so it's also hard, and it's also hard to implement like an efficient checker to like check the certificate in like in an efficient way. So I'm proposing definitely to reuse as much resources and things as possible. And it basically gets us to like a unified system where we just reuse the same checker for like all problems that we have. And with RVB, we can do this for a lot of combinatorial optimization solvers, and we even get formally verified guarantees of correctness of the results. And that's all for this talk.
Any final questions for Andy?
How much do you usually save by trimming in practice? Or like
Depends. Like sometimes you don't save anything. Sometimes you can like almost get rid of the whole proof. Like then you're only a few percent that's left. But it depends definitely on the proof. That's because like the proof could be already like very efficient in the sense that your solver is does the right reasoning so that it doesn't do like a lot of stuff that doesn't get itself to the conclusion, but it gets to the conclusion rather quickly or like in a direct way.
Yeah.
So it already finds like the minimal proof or like that's so to say.
Is it more solver dependent than problem dependent?
It's more it's both,
Okay.
but yeah.
Can you talk about the decision to have VeriPB kind of be responsible for the elaboration? Like, why not just say, hey, if you're writing a solver, please, because you're already as a solver writer implementing this thing. Why not just have them elaborate on their side?
We thought about this, and sometimes we do this. Sometimes we actually output elaborated proofs, but it's very rare. The main reason is that it's easier to write with the syntactic sugar rules, to write a rule, to write a proof to get in this. Because then like you don't need to elaborate like every conclusion for like the strengthening rules. Like you can just say like, okay, all of these, like I have all my constraints and they are like, all of them are like, they are obvious. Why should I like give like details and I leave that to VeriPB to figure out the details of the cutting planes derivations for like strengthening.
Okay.
So it's mainly just laziness and having it as easy as possible to write certificates and to make it easy to adopt. But you could do it. You could also just directly write elaborate proof.
But I mean, it's two comments to this would be one that if you try to get adoption of this proof logging techniques, then from the user side, if you talk to people who actually work in combinatorial optimization, then they perceive VeriPB to be a complicated proof system. Like already today, it's hard to write VeriPB proofs. With all of these syntactic sugar, it's still, I think it's fair to say that people are complaining that this is too complicated, like too much overhead. And then I think also if you're looking at, so we didn't talk about that, but if you look at stronger paradigms like constrained programming or say subgraph solving, then you have the problem that the solver has its internal representation of maybe the graph of constrained program, and then it's writing the proof down in the pseudo-Boolean form. And then the solver might know roughly what the translation looks like, but it would be quite costly to know for every constraint exactly how I translated it and which constraint has which number and so on. And so
I see.
forth.
Yeah.
And so you now know that, well, I know now that this constraint here will propagate X to true. Like the solver has established this, it knows it's for a fact, and it is for this general reason. It is because of this constraint, and it's obvious, and so you just have to use this pseudo-Boolean coding and stare at it, and you will indeed see by this reverse unit propagation that if you try to set X to the wrong value, you will immediately get contradiction.
Mm.
And already like realizing this can be somewhat complicated. But now, if in the solver, in addition to doing this high-level reasoning, you would have to do the low-level bookkeeping to match up exactly which constraints would give you a cutting planes derivation of this fact, where the cutting planes reasoning is like extremely far from what the, say, subgraph solver is doing.
Right.
Then that would probably be so much extra bookkeeping that people would just say, no, I'm not willing to do that.
Mm-hmm.
And so, for instance, if you look at the early papers, like what happened when this pseudo-Boolean proof logging started to take off, even in the first place, somewhat, was the killer application that made this even possible was reverse unit propagation. Before that, we already knew that yes, it's possible to write these proofs, but even like the dedicated applied combinatorial solving people who believed in proof logging, they said, yeah, we understand. Yes, in principle, I can write this cutting planes proofs, but it's just, my brain will explode.
Mm-hmm.
And then we figured out, oh, but wait, this reverse unit propagation thing that they do for clauses, we can actually express that in general for 0-1 integer linear inequalities. And then suddenly, okay, yes, now I agree. Now I'm willing to like, it's still a lot of work to write my proofs, but at least now it's doable. Right. Before it was even like beyond so complicated that I'm just not going. No. But I think I will for our own solver. I don't know if we're in principle almost.
Yeah, I think it's just maybe
writing
some minor syntax things, but no major conceptual hurdles that we would have to come over to write elaborated proofs with.
And then the reason for writing the elaborated proofs is that would be like, then you have a much faster checking process.
Mm-hmm.
So it's like a trade-off, ease of use, how speed of checking, what are you going to do with the proof? Is this like a one-time thing? Is this like one reason for trimming, as Andy said, like if you want a really short proof, maybe you can store it somewhere. Mm-hmm. This is actually interesting. This is something that, for instance, Amazon Web Services is doing. They're actually generating proofs and storing them, not in the very PV format yet. Let's see. They're using other format, but because they have convinced the auditors that as part of their safety and security work, like guaranteeing that they have all the access permissions and so on and so forth set correctly when you have all of these different programs that are running on the same cloud and nobody should have access to anything other than their own data.
Mm-hmm.
These properties they actually prove with proof logging. And then they will store these proofs. And so that the auditor can like make spot check and say, let's see if this is correct.
Mm-hmm.
Basically fire up the proof checker. And that, yeah, that's pretty cool. And that's the reason why then you're willing to spend some time to minimize the proof because you're going to store a lot of. Sorry, is it?
Yeah.
Side remark? Okay, what do you say? Should we call it a day?
Yeah.
Thank you so much, Andy.